Have you ever stopped to think how some really complex digital systems, the ones we use every day, are actually built on these incredibly elegant, almost simple ideas?
It's fascinating, isn't it?
Yeah. So today, in this deep dive into computer science and software engineering, we're digging into one of those, the leaky bucket algorithm.
Ah, yes. Oh, a
It's, absolutely crucial for managing how data flows,
Yeah.
like streaming video, huge cloud systems, all that stuff.
And it's not just about control, really. It's more about elegantly smoothing out unpredictable, kind of bursty data into a steady, manageable stream. It's basically a cornerstone for network stability
Right. So the core idea is this bucket. Yeah.
with a constant leak.
Exactly. Imagine pouring water in, maybe sometimes a little, sometimes a lot, but it's always draining out at a steady pace.
Right.
Pour too much in at once or pour faster than it leaks on average?
It overflows.
Precisely. And our mission today is to unpack how that simple picture translates into limiting actions shaping network traffic. We want you to walk away with a quick but solid understanding. Okay, and what's really interesting, I think, is that this one algorithm is actually seen in two pretty distinct ways.
That's right. You've got the leaky bucket as a meter, and then the leaky bucket as a cue. They sound similar, but they function quite differently.
Let's maybe start with the meter version. What's the fundamental idea there?
Okay, so the leaky bucket as a meter, like Jonathan Turner originally described it, is basically a counter. Or you can think of it as a variable that sits outside the actual flow of traffic.
Outside. So it's not holding the data itself.
No, not at all. It's purely a check. Like, think of it checking conformance. When a packet arrives, the counter goes up, water added. Then steadily, the counter goes down at a fixed rate, water leaking.
Right.
And the key is, if that counter stays below some set limit, the bucket doesn't overflow, then the traffic is considered conforming. It fits the rules.
So it's strictly a measurement thing.
Yeah.
Check.
Yeah.
That's interesting.
Yeah.
What's the benefit of just measuring traffic like that instead of, buffering it? Where do we see this?
Well, the big advantage is policing and shaping without the overhead of actually holding packets, potentially delaying everything. It's used a lot in traffic policing.
Policing meaning?
Meaning, if packets don't conform, if they'd make the counter overflow, they might get dropped or maybe marked as lower priority. This protects the network from getting swamped. Think ATM networks back in the day, where that kind of predictable delivery was absolutely vital.
Okay.
It's also key for traffic shaping, where maybe instead of dropping, you just delay the packet slightly until it would conform. Let the counter leak down a bit first.
Ah, okay. Delaying instead of dropping.
Exactly. And, beyond just network traffic, this leaky bucket counter idea is handy for spotting weird patterns in other areas, like detecting sudden bursts or even slow increases in things that should be random, like maybe memory errors in a server.
Huh. Like an early warning system.
Sort of, yeah. Spotting trends.
And to make this meter work, what are the knobs we can turn? The settings.
Right, the parameters. Well, the main one is the emission interval. That sets the average rate limit, your bandwidth, basically how fast the counter leaks.
Your leak rate. Got it.
Then there's something called the delay variation tolerance, usually written as tau, the Greek letter. This is basically a measure of flexibility. How much earlier can a packet arrive than the strict average rate would suggest? It controls jitter.
Jitter being the sort of uneven arrival times.
Exactly. You want a smooth flow, not packets arriving in clumps, then big gaps. Tau helps manage that burstiness. And finally, based on that tolerance, you get the maximum burst size, or MBS. That defines the biggest chunk of data that can arrive all at once without overflowing the conceptual bucket.
Okay, so the meter measures, checks conformance, allows for some burstiness with tau. But what if you really need to enforce a strict, steady output?
Aha, yes. That brings us to the other interpretation. Andrew Tannenbaum described this one, the leaky bucket as a cue.
How's that different?
Fundamentally different, because here, the bucket is the buffer. It's a simple FIFO first in, first out queue, right in the path of the data. Packets go into the queue.
And then they get let out.
Exactly. They're pulled out and transmitted at a fixed, constant rate, just like water leaking steadily from a real bucket. It directly imposes that smooth output.
So it physically holds the packets and releases them slowly, like a very orderly queue, a polite bouncer maybe, letting people in one by one.
That's a pretty good analogy, actually. It definitely enforces strict conformance. It smooths out all the burstiness, removes the jitter completely from the output stream.
But what's the catch? Being too rigid, maybe?
That's precisely the downside. Its rigidity makes it potentially quite inefficient, because it transmits only at that fixed, often slow rate it can waste network resources.
Oh, so.
Well, if the incoming traffic slows down, the queue still only sends packets out at its fixed, slow leak rate. Even if the network link itself, the pipe could handle much more. It prevents flows from bursting up to port speed when capacity is available.
Ah, so you're artificially slowing things down even when you don't need to. Wasted bandwidth.
Exactly. Wasted capacity, potentially slower experience for the user. You do see it used, though, in specific cases, like Nginx has a module that uses this idea to limit concurrent requests.
Right. Okay, so two distinct versions. Now, you mentioned a deeper connection earlier, even involving another algorithm.
Yes. This is where it gets really elegant, I think. The Leaky bucket as a meter, the counter version, it's essentially a direct mirror image of the token bucket algorithm.
Mirror image. How does that work?
Think about it. Token bucket adds tokens, permissions, at a steady rate and removes them when a packet is sent. Leaky bucket meter adds water usage when a packet arrives and removes it at a steady rate. One adds permissions, the other tracks usage against a limit. Fundamentally, they're describing the same constraint mechanism, just from opposite perspectives.
Wow. Okay, two sides of the same coin.
Pretty much. It shows how these core ideas in traffic management are deeply related.
And there was another connection between the two leaky bucket types.
Yes. The leaky bucket as a queue, the FIFO buffer version, can actually be seen as just a special case of the leaky bucket as a meter.
A special case. Yeah.
Remember the delay variation tolerance, the meter version? The flexibility parameter?
Yeah, controlling jitter.
Okay, now imagine setting that tolerance to 0. Yeah. No flexibility. Packets must arrive perfectly on schedule according to the average rate. Any deviation makes them non-conformant.
That sounds very strict.
It is. And what happens when is 0? The meter effectively forces a perfectly smooth, non-bursty output. It behaves exactly like the rigid FIFO queue version. So the queue is just the meter with 0 tolerance for variation.
That's neat. Ties it all together.
Yeah.
So bringing this all back, what's the big takeaway for, people building and using these systems?
Well, the leaky bucket algorithm, whether you think of it as that precise meter checking things or the simpler queue smoothing things out, gives us really essential tools. Tools for managing data flow, keeping networks stable, optimizing performance. It's fundamental stuff in computer science and software engineering.
Absolutely fundamental. Okay, so that leads us nicely to our final provocative thought for you, the listener. Given these two versions of the leaky bucket, and especially those trade-offs we talked about, strict control versus maybe wasting resources, how do you think these foundational concepts are still shaping how networks evolve today, how we handle the crazy, diverse, and demanding data loads we see now? Something to ponder.